I am the program chairman for the local Rochester chapter of Imaging Science and Technology. We try to have a speaker series with speaker once a month. And Wayne will be introducing Mark in a few moments. In November, we will be down at RIT at the Munsell Color Lab, and Susan Farnan and one of her PhD candidate students will be talking about multispectral imaging with a program they have called Beyond RGB. Then in December and January, we have back-to-back talks about sensors involving how they're putting AI processing directly into the imaging sensor. And January, we have another talk where they've optimized sensor designs for imaging. So thank you all for joining us, and I will turn it over to Wayne.
Good. Thanks, Roger. Hi, I'm Wayne Prentice. I'm a recording secretary for the local Rochester IS&T chapter. Good evening, and thanks for joining us. So last summer, we had an afternoon of really intense weather. There was a risk of significant risk to tornadoes in the area. And during that time, WHAM weather forecasts used radar function never seen before. They showed the contrast of wind speeds to isolate where the winds were colliding in a way to identify a tornado risk. I'd never seen that before, and it made me curious what other cool tricks exist. So the next thing I wondered was, who would I ask? Well, that was an easy question. Many months ago, my wife saw a strange light streak in the sky, and she reached out to Mark McLean to ask what it was and got a nice response. So it's obvious to me that Mark was the guy to go to ask about weather radar. So Mark brings us the weather most every day, forecast here in a very complex Western New York market, and he makes the weather very accessible to millions of viewers. And so we're very grateful and honored to have Mark here tonight to show us what shows can tell us more than just where it's raining. So thank you, Mark, and I'll turn it over to you from the WHAM Channel 13 Weather Lab.
All right. Thanks again, Wayne, and thanks, Roger, and thanks everybody for being patient here. My apologies again for kind of sitting in late, but to be public speakers, as scientists and engineers, right? Oftentimes the hardest thing to do is to communicate the things that we know and understand to others in a way that they can understand it. So that's always been the challenge in meteorology. In a 3-minute weather forecast, we're trying to convey all that information. And if anybody has a question at any point, I can see just names and across, but maybe go through Wayne or Roger and just let them know that you have a question on something that we're looking at, and I'd be happy to answer any questions as we come on through. But the thing about the radar that came in, and I started thinking about this, I said, well, what would a meteorologist have done back in the 1920s, 19-teens? You go back a ways without this technology that we just take for granted today. I mean, we use it to scan the atmosphere. There's dual pole radar, which we're going to look at today, that the National Weather Service has installed across the country. Different ways of looking at hydrometeors. That's what precipitation is called in the atmosphere. So that's the technical term for weather when you go through and study it. But what was the first practical application? And oftentimes it comes back to Pearl Harbor, and we had just a conventional radar installation there. It was still a new technology, not tried and true yet. And this new technology actually detected some of the squadrons of zeros that were coming in for Pearl Harbor that day, and instantly the world had changed. We could see things that were too far away for the human eye to see using something that's going through the atmosphere at 186,000 miles per second. I mean, it's literally going out, and the more powerful you made it off the dish that was sending the signal, the farther that signal would attenuate through the atmosphere. So this became just an incredible technology for weather, even though its original case use was for more of a military use for it, which is obviously still the case today and at airports today. But as mentioned, we were talking about all sorts of severe weather. New York State has had, I think it's 31 tornadoes this year. We smashed the all-time record for tornadoes this past summer. And some of them were fairly large, and some of them were spinning. And I'm going to look for a video here before I share screen just to make sure I have it pulled up. I've got birds in a hurricane. And don't let me forget to show you birds in a hurricane. You remember Hurricane Milton that just devastated Florida. I have to show you a view of that. But let me see if I can pull this up on the fly. It's probably going to be difficult to find if I don't have my weather folder. There's the photos. Funnel cloud along, there it is right there. This stuff never works on the fly, but this is going to work for us. So I'll show you what this rotation looks like in just a second. Let me pull up birds in a hurricane. Also something that you'll probably want to take a look at. But I'm going to share screen if I can. Let me go to
I think I
share.
enabled that for you.
Okay. And this should be screen number 1. Let me share that. I think that this is one of the, can you see these? Okay, it looks like you can see it, right? The Jetstream Max dual polarization screen.
Yep,
Perfect. This is great. Okay, so what we have here is, let me make this one window bigger, is a description from NOAA. I teach at Monroe Community College. I teach an intro weather course and intro weather lab there too. And I like to fall back on this description. It's just excellent. This whole series that's called, quote, Jetstream from NOAA. This covers any range of topics in weather that you could imagine. And you're gonna be amazed at the level of detail they get down to on the radar here for the National Weather Service. But just to take you back away, we had something called Doppler, and I know as scientists and engineers, you're used to the Doppler effect, the shift that you can detect as an object is either moving towards you and away from you. And this goes back to the 1980s in weather radar. And it became the first time where we could give folks up to 20 minutes of a warning that there was a spin detected in the atmosphere. You know, you take yourself out to Kansas or Nebraska, these places in Texas and Oklahoma that get tornadoes all the time. And these folks, you know, at times would only have 3 to 5 minutes of warning with conventional radar. That's it. And you can imagine, you know, the fear and panic, you know, as a tornado warning would come off the NOAA weather wire or your weather radio at home at the time and say, you know, tornado basically on the ground. Whereas now the Doppler radar and upgraded dual pole radars since then gave us that ability to increase the lead time for viewers and the audience to get to safety during these extreme weather events. So it was super helpful. But just to bring you in here, it's something that we look at for 2 channels. So basically what's happened, you get a side scan on the radar, and you also get a vertical scan on the radar as it's shooting out from wherever the beam is sending off from. For us, by the way, that's Buffalo. Binghamton would be the next closest after that. Montague, which is up on the Tug Hill, if you've ever been out that way, also has a National Weather Service radar. Unfortunately, Rochester kind of falls in the middle of all those areas. So as you understand, radar has to be sent out with a beam that's slightly tilted up so that it doesn't hit obstructions like trees, tall buildings, hills, that kind of thing. And you'll see that on our broadcast. You'll see the wind towers and the clear air turbulence that shows up on the radar down in Wyoming County. As those blades spin around, the radar gets kind of tricked and fooled down there. So we can't ever clean up that image. There's no way of doing it. But because we get a side scan and because we get this vertical scan, there's very little that we miss in the atmosphere anymore. And with that ability to go up and down and back and forth, you get outputs that look like this. This was a supercell thunderstorm in Wiley, Texas in 2016 in April. And you see these reflectivities that come off of this, and it's indicated in decibels. Basically, the bigger the dBz, the bigger the striking object in the atmosphere. And you take yourself out to Texas, they can get like 3 to 5 inch hail. I mean, stuff that you couldn't even imagine. Although we did have a storm this past summer that put down 3-inch hail in West Bloomfield. It was unbelievable in one of those storms. I think it was back in July. But when you look at this, this is a large indication of hail. When you see that circled area on the left and that yellow circled area, that's where they were getting, you know, a storm that produced over just $1 billion in damage from hail. And it's one of the biggest killers in weather for livestock because you can't get for farmers out there, they can't get their agriculture back inside the barns the cows and whatever else is out there in time when these big storms hit. So it's a huge loss. Obviously, in Western New York, the concern for us is more of the fruit farms and the apples, the peaches, the plums. They can be damaged and bruised up by large hail. But this is the radar helping us out and saying this is what's coming in at us. Now, when you look at correlation coefficient, this is one of the coolest parts of radar, and I'm hoping that I can actually pull this up on the Zoom call here with the actual software that we use on television in just a second. But basically, what we have the ability to see now goes way beyond weather. So on the boring nights of summer, we can look at mosquito swarms going across Lake Erie. It's amazing. We can look at tall buildings if the radar is scanning down. Any kind of bugs. We can look at wildfires in progress and the plumes of smoke that are going up into the atmosphere through wildfires. We can also look at, of course, I mentioned hail, but also sleet and freezing rain and different types of precipitation that have different correlation coefficients that come back. So this goes on a scale from 0 to 1. And basically anything that's low is ignored, or it's kind of not presented, is another way of saying it. Although we could present it, the computer software says that's probably birds or a flock of geese in the atmosphere. I don't want to share that with the audience. It's not particularly relevant. I was a meteorologist in Syracuse, and I can tell you firsthand, this was awesome. In a really boring October weather day back in 2003, we had a private radar that WSYR television owned out there. And it was scanning out over Lake Ontario. And there was this huge flock of geese that was coming south across Lake Ontario. And of course, the radar was all over it. And we started getting calls from people. They say, you got to see this. This is one of the biggest flocks of geese we've ever seen. And we ended up sending a photographer out to shoot it because so many people saw it and commented on it, and then showed the radar scan in a loop mode that actually showed the progression of these birds from the north to the south across the area. If you watch Marty in the morning here in Rochester, sometimes he'll also show the morning bird launch from Montezuma Swamp. He can actually show that again on the slower weather days we're talking about here. So I know I kind of talk fast. Just let me know if anybody has any comments or questions on anything I've said to this point. But that's one of the more useful parts of this new radar. And the other one is the tornado debris signature. So when tornadoes lift debris up into the air, there's whatever it is. It's trees, it's pieces of barn, it's pieces of homes, sadly, that get lifted up into the atmosphere. When you get these larger objects, CC drops significantly. So a tornado debris signature back in the National Weather Service office, the meteorologists that are working there can actually look at a low correlation coefficient and say, well, there's a strong rotation here first because we have the Doppler that can detect inbound versus outbound towards that radar dish. And then you can also see things like that. So where you see this arrow in the upper left picture, this is where we're getting a tight little spin. And I'm actually going to show you a video of this from a tornado that developed near Lake Ontario. Let me see if I can, let me go to that right here. Let me show you what it looks like. Okay, so there, this green and red, when you see this green and red inbound versus outbound, and this was right along the Lake Ontario shoreline. So what this indicates to us, and this is simplified and kind of pulled down a little bit, if you will, for television and our audience. When you see green, that means that the information that the radar is detecting shows a shift back towards the radar dish in Buffalo. So whatever's there is going back towards Buffalo. Now where you see the reds on here, and this is a National Weather Service data table. So this would be one that if you moved out to the Midwest or someplace else that gets lots of tornadoes, that you would be able to see. I can probably blow this up a little bit more too. There you go. Now it's full screen. Okay, so in there you can see that right along the lakeshore. So what we ended up having here, we had a thunderstorm that produced a downdraft of cold air. It hit the surface, it spread out, and at the same time the Lake Ontario lake breeze was coming in off the lake, and the two hit, and where the two hit, they started to spin, and that produced this this area of damaging storms. This went through parts of Webster. It ended up down into down into Wayne County. But we watched this, and I was working with meteorologist Scott Hetzko in the office at the time, and we said, yeah, this one's probably going to be trouble. Anytime you get a signature like that, and it's very strong in a very small area, that indicates that there's a decent spin in the atmosphere, and that you could have some real trouble in that spot. Here's another thing with the correlation coefficient. Let me see if I can. I guess that's as big as this image is going to get here. This was Milton, and this was the eye of Milton just last week. All of these little bluish slash yellow slash whatever the other color tables are in here in the middle of this hurricane. Hopefully I'll never have to use this in my life. Okay. But what you're looking at on the inside of this are birds, migratory birds, some, birds out to sea that got stuck in the center of this hurricane. And you're actually looking at that on the scan from the radar, and the radar is capable, of course, of picking up those objects. Would usually ignore them. So when you watch on our broadcast or wherever, a national outlet like the Weather Channel or something would have had a radar loop going and a satellite loop, they would have showed the whole spin of the storm going. But within that, this would be something that probably would not have been shown, that the radar is certainly capable of seeing and pulling up an image like that. So does anybody have any questions on either one of those two images, or the radar loop there that I was just able to play? Anything at all popping into your mind?
Yeah, two things.
Sure.
First thing, Joe posted, what is the time between each image you see, and what is the sweep time of the radar?
What is what was the first question again?
What is the time between each image that you see?
Okay. So if I go to here, yeah, I've got a loop that's about one hour long. So the radar in a standard mode would sweep around 4 times in a minute. Okay. So basically every 15 seconds. Now they can spin that up dramatically if there's a storm in the area, and the tilt level goes up also. So it'll start at a very low tilt elevation, and the tilt level goes up 0.1 of a degree or so on the second scan, maybe 0.3 on the, they go up to about that high. You don't want to go up too high because then it just shoots out of the atmosphere pretty quickly. So they usually stay pretty low to the ground. So if that loop right there just had the minimum of 4 scans in an hour time, I'm just doing some fuzzy math in my head. What's that? 240 separate scans on that one particular loop that just went on by right there. So this is something that comes in almost in real time to us. Obviously, if I was sitting at the National Weather Service office in Buffalo, I would have real time access and information to this. We go through a third party vendor, as do most television stations that don't have their own radar, to get this information that we can share with our audience. So that's an interesting question. So does that get to the heart of that one?
I'm going to guess yes.
Okay.
So the second one.
Yep.
Yes, thank
Talk
you.
a little bit more about the correlation coefficient. What 2 data sets are being, or what multiple data sets are being correlated to look for to compute that correlation?
Okay, so on the correlation coefficient, so it's of the 3 dual poles, base product this would be the most likely one to be used to detect an object in the atmosphere if you were going to this. I have never in my life used this one time on the air in Rochester. I haven't had a use for it. We would go to the velocity scan, which I just showed you. The inbound and outbound usually takes care of any real severe weather that we get. But if we did have a tornado and a debris ball that ended up showing up on the air, is a measure of how similar the horizontal and vertical pulses become after hitting a target. Okay, so if the pulse to pulse change is similar between horizontal and vertical, then the CC is high. So that just means that it's probably precipitation. So a lot. When you think of like sleet or something, they're little round balls. It doesn't matter if you're scanning it vertically. It doesn't matter if you're scanning it horizontally. Both of them are going to see little icy pellets up in the atmosphere. But if you're seeing, a 2x4 by 8 flying through the atmosphere, very likely the scan on the vertical is going to look a heck of a lot different than the scan on the horizontal as it catches that tumbling through the atmosphere. So that's one way that the correlation coefficient can be used to sample the atmosphere. So
The phenomenology is related to the symmetry, vertical versus horizontal symmetry of the objects.
yeah, and if they increase, I don't remember how many times they can safely spin the radar in a minute. I want to say it's 16. Don't quote me on that though. But it's a much faster cycle when we get into storms, and that you can get, if there was a debris ball, they would be scanning it very quickly. And they also don't have to do a radial scan. They can also just sample. They can also stall the radar and just set it on one spot and range that one particular supercell thunderstorm that's producing the tornado or the severe weather in the area. I'm sad. We used to have our own radar here at the station. Technically, we still do. It's up in the tower. It's an old conventional radar. When I started here, we could use it through about 2010. One of the most, it was not a Doppler radar. It was just conventional. So one of the best things we could do for that was lake effect snow, because lake effect snow forms at an elevation much lower in the atmosphere than our other storm systems would produce. So, the storm that's coming through this evening, I call it a storm. It's a little trough of low pressure. It's going to make a little rain. It's not a big deal. But the rainfall with that would go up, thousands of feet into the atmosphere. Sometimes when we get to January and February, the atmosphere is so cold that the atmospheric moisture content is so low that the lake effect snow is forming under 1,000 feet in the atmosphere in the coldest, driest air masses. And by the time the Buffalo scan and the Binghamton scan get here, they're between 4,000 and 6,000 feet high up. They're going to shoot right over the top of it. So that was the advantage of even just having a conventional radar here in Rochester, was that we could still sample the lake effect snow in the wintertime that was coming down. So that was a great use for it. But once we went high definition, the cost to upgrade it was exorbitant, and the people in power decided to make a decision, and unfortunately here we are, but I'm not complaining.
Very good. Thank you.
Yeah. Any other questions on the list there for that? And then I'll actually show you the live view of this that we would use on TV. So let me skip over to that. And this is today. This is right now. Sometimes when I'm sharing on Zoom, the camera will cut out because this program that we use likes to steal the camera. So this is a 30-minute loop. I just want to warn you in case I disappear here. The audio won't go, but sometimes the video gets stolen. Let me go to right now. So this is a program that was developed by IBM, and it's called Max. It's called the Max weather software, and most meteorologists in the country use something just like this. And when you're looking out today, it is detecting some of that precip that's out over Lake Ontario. So this area right here. Okay, this part of it, as you notice, in this huge area out over Lake Ontario, is all inbound to the Buffalo radar. This area over here is almost exclusively outbound to the Buffalo radar. So that means that everything is moving pretty much in a linear fashion. I wouldn't scan this or even worry about something like this to produce there's not enough energy in the atmosphere tonight anyway to produce thunderstorms. But even if there was, a view like this wouldn't be particularly concerning. But what you can see is the progression south over the lake over the last 30 minutes of this on what we would call storm rotation or radial velocity on this. So as you look at this image right here, does anybody have any questions on the information that is up to the minute here, 6:57 p.m. or do you want me to zoom in on something that you might see? Here's the wind towers I was just talking about down into Wyoming County too. Notice how as the beam goes through there, it's detecting all those, and you can see the little, watch them spin. See them spin down there? We got bad data frame there on the front end of that, so that's not all switching from inbound to outbound. But of course, the towers sit still, so you get a good look. You get a good look at them right there.
So all the Doppler scans are always in the context of particular radar. So in other words, if you had a radar that was on the east side of this, we would see the colors reversed.
Yes, and because the velocity scan uses so much information. I am only able to use, I'm able to use 12 live radars with sweeps like this at a time on TV. I am only ever able to use one on a velocity scan because the amount of data that's coming off of that dish and being processed is so large that the vendor that we have only allows us to have one. So we always default it to the Buffalo Doppler scan so that, you know, we get something that's within 60 to 70 miles of Rochester right there. Yep. So that is one radar mode right there. So on days where I'm using this one, those aren't my favorite days. I'll say that. So you're probably wondering about other radar modes. So we have a table, and I can go to this this table down here, sweeping radar. You're getting a lot of inside baseball here. Here's the other dishes that I have data for that I can actually show you radar imagery for. Notice that at the top right, and I'm not sure if you can see it on the screen, it says 3D volumetric storm relative mean velocity. So that's what's defaulted to this particular image. But I also have information coming in from Binghamton, Cleveland, Montague, Exeter. That's in Ontario. We use that to catch connecting bands of lake effect snow in the wintertime that are coming in from the northern Great Lakes down towards Lake Ontario. Detroit, Albany. We switched last week, and I got to switch these back. I forgot to do this. We switched to Orlando and Tampa radars, live scans. We were showing those on the air as Milton was making landfall last week. Upton, of course, New York City area, Pittsburgh, and State College. Sometimes we catch some weather coming in from those areas, and it's useful to see. But I can show you, these are all the data tables that I could put on the air at any particular spot. There's reflectivity. There's reflectivity with precipitation type. I love this for the wintertime. And it's picking up some. Can you imagine? Oh no, this is the Montague radar picking this up. Sorry, I talk to myself sometimes. Right here, don't ignore the legend at the top of the screen. I'm just going on the fly here. What you're looking at now is reflectivity with precipitation type. And anything that's green or yellow on here is rain. And anything that's bluish or blue is a different type of hydrometeor in the atmosphere, and that is in the form of snow. So they are getting some snow, and I can loop that for you, kind of show you where it's drifting off to. If you like the Adirondacks, it's up really into the almost into the central Adirondacks there. Long Lake just west of there, south of Tupper Lake there, south and southwest. So picking up different types of radar right there. We can do correlation coefficient. Let's see. Again, everything is uniform. There's nothing too crazy about any of this. So it's just seeing the either drizzle or ice crystals well up into the top of the clouds as it's scanning. You're seeing a little bit of scatter out over Lake Ontario, and you're seeing a different type of correlation coefficient down towards the wind towers there. Of course, down towards Wyoming County, where you've got the windmills spinning away tonight on that northwest wind. So you get to see this. How many times have I used this on the air? Ever? Zero. In the Midwest, when you've got debris balls and debris signatures for tornadoes, you're using that on the air. There's no doubt. I already showed you velocity. That's the velocity scan. Spectral width differential. I've never used that. Never used that on the air. Let me load up a different type, and this is a lower resolution radar. It's not happy with me right now because I'm loading a lot of different data sets all at once. Let me go to this, and I'll scrape off the arrows I just used at 6 o'clock. This is called the NowRad, and I've got a satellite image loaded on top of it also. Also capable of displaying different types of precip as they may be up towards Quebec, north of Montreal. It's got a little bit of a different color scheme with it here for some of the snow that's coming down up there, and again into the Adirondacks. This is what's called a composite image. So I like to use this less than just a single site image, because what this does is it allows the computer program to overlay the different radars on top of each other. And sometimes it, quote, overdoes it. It makes it look like it's a lot worse than it actually is because it layers all of these stacked up kind of like an ice cream cake so that you get those images right there. But any questions on any of these kind of different types? Because we're kind of getting into the meat and potatoes now.
It's good stuff.
thankfully, we've got some weather here tonight to show it, and a look at a spinning storm that we had from one of those severe thunderstorms back in the summertime. But this is, this is the whole network of it. It goes all the way across the United States, Canada, parts of Mexico. I don't think we have a contract with Mexico to get some of their data. You can see it's down into Cuba. This would be the Key West radar down there, showing some thunderstorms over Cuba, scanning out that far away. There's another boundary down here that's putting down some snow showers into parts of the Appalachian there. So we're getting that information too. And you can see the low, actually. If you look by Quebec, you can see that counterclockwise spin if you look really closely. Sometimes the radar gives that up just by looking at where the precipitation is going. You can kind of pinpoint the surface low pressure system just by watching a radar.
Is the precipitation type encoded by the correlation coefficient?
I don't know how much. I think it is. I think anything that goes beyond 0.8 is relatively kind of smooth and characteristic. So anything between 0.8 and 1.0, the radar is really satisfied of what it's seeing falling down. So in this case, it's the rain tonight. It's some of that wet snow off to our northeast. If we looked at all those, I don't have a legend, unfortunately, for the I've never built a product for this for correlation coefficient. But if I did, my guess is that it would be somewhere between 0.8 and 1.0. The highest confidence or lowest, if you want to look at it like this, lowest irregularity of any of the objects that it was striking.
Oh, so my question is for the snow versus rain versus sleet versus grapple.
Yeah.
It knows which type it is because of the correlation coefficient?
Yes, yeah, it'll pick it out, and it'll pick it out on the horizontal scan and the vertical scan as it goes through and gets sampled. So as precipitation starts to transition, so let's say we've got a warm front coming through western New York, and out ahead of the warm front, the air is still cold. Snow will be a fairly uniform area of snow will develop out ahead of that, and the radar will scan that, and that whole band will have a very similar correlation coefficient. Right behind that, as it starts to transition to sleet and freezing rain, those objects would have a different texture to them, a different feel to them in the atmosphere. And then as you get over to plain old rain, it would also transition back to something very similar for that. Yeah, definitely.
Mark, can you see the chat window? There's a couple other questions on there.
Oh, sure. Let me see if I can get to that.
If not, I can read them to you.
Let me see if I can pull those up. I just saw it pop up. Oh, there we go. Chat. Sorry about that. I didn't know what. Okay, so Joe had what is the time between each image that you see? Okay, so we were talking about that along the lake. Is there capability to determine altitude? Yes. Actually, these are all 3D isometric surfaces. So let me go back to that. That's a great question. I actually have to, let me move your chat over here so I don't lose it. Let me go back to the quote live scan right here. Actually, I haven't pulled this up yet. This will be the one that'll show you the intensity there of some of that coming down. Let me pause it and let's go in. Maybe we'll get something near Oswego. So I'm able to use, this is a 3D volume box. Sometimes you'll see us use this for thunderstorms. I love showing people how, quote, how tall up into the atmosphere something is getting. And this is, as expected, the atmosphere is so cold today that none of this stuff is going above 10,000 feet, which, by the way, for lake effect would be decent. But if you look closely, we've got a legend or a key there that goes from 10 to 60 up into the atmosphere, and the radar is scanning up. It looks like about 12,000, maybe 13,000 feet for some of those areas out towards Oswego. I can hit another spot, maybe closer to home. Let's go towards Wayne County and another volume box here. See this stuff, and some of this maybe even up higher. Now, when we get those and we do this occasionally in the wintertime too, or late fall, when we get those solid bands of lake effect snow coming in off Lake Ontario, you'll get some of those that will go up to 22,000 feet in the core, sometimes 25,000 in the core of that band. It is just an active line of thunderstorms as that heat and moisture is being lifted up off the lake surface into that solid band of snow. I've seen something like that. I went to Oswego, by the way. That's what got me into weather. I forgot to mention that at the top. I usually start with something like that, but I wanted to dive right in because I had missed the start here. But that's a great question. So hopefully, Roger, that helps out. Why do we seem to have so many stalled weather systems in recent years? Joe, it just depends on quote where you are relative to the storm. We always have that saying that weather is local, but we've had some slow moving systems. It depends on what the jet stream does. If a storm gets quote cut off from the jet stream, that's not a great scenario. Depending on what that storm is producing, you're going to get stuck with it for a long time. So we have cut off lows in weather that sometimes produce weather like that for long periods of time for folks out there. But even, let's go to right now. Even if you went into the Adirondacks here, like just for kicks, I want to do a volume box on this snow. It's probably going to be pretty low. It's not even showing. Yeah, you can barely see it if you look really closely. It's at about 5,000 feet up there. So the atmosphere is so cold that it's producing that look up there. Good stuff. Yeah, good questions. Any other questions out there? I loaded up a couple of different products. I like the National Weather Service Explainer the most. It's really very thorough on jet stream. And again, if you have any other topics that you like to get into, it's a good site.
General weather question.
Sure. Yeah, I'll take any of those, and I can talk about the office too for a little bit if you'd like. I can handle any questions that you want to go to, really.
So when engineers and scientists, whenever we hear a probability, we also want to know the confidence level of that, right? So when someone says there's a 75% chance of precipitation, what does that mean?
Okay, so that to a lot of people is a little bit tricky. So if I went on and let's say I think we had 60% out for today. So it depends on the forecast time interval for today. I would say for most people, that's probably when they're up and driving on the road, or the kids are going off to school, coming back home, maybe like an 8 to 4. And then the evening forecast for me this time of the year is like a 4 to 8. And then the overnight for me starts to go like 9 or 10 to 8 a.m. So if I said a 60% chance of rain for today, that means that if you picked one spot within the forecast area, which for us is Orleans, Genesee, Wyoming, Monroe, Livingston, Wayne, Ontario, and Yates counties, that means that there's a 60% chance that one spot within that defined area would have that type of weather that I'm describing in that time interval. Hopefully that makes sense.
It does.
Okay, because that's a lot.
Yeah. And is there a confidence level on that?
So the confidence level would be expressed through that, what we call that POP, the percentage of precipitation. It's not set in stone, it's weather, and it changes. But if you ever watch a forecast that has a 0% chance or a 100% chance, the meteorologist that's delivering that forecast has a very confident forecast. Okay, once you start to get around 50% or so, the confidence in all the spots in the area of seeing that actual weather starts to drop significantly. Yes. Yeah.
Excuse me, but the way you described it is you pick any one area.
Yep.
And it's the probability of that event in that one area.
In that one area.
But you have a large listening area. So
Yep.
If Webster has 100% chance and Spencerport 20%,
yep.
What do you forecast?
Well, then you just have to blend it. You have to take a blend, and that's basically when you watch the 7-day forecast, that's a blend of the 8-county area. Okay, so we can get more specific on things like, let me show you. Actually, I'll take you over to maybe the smallest. This is the highest resolution weather model that I have. It's a 4-kilometer grid scale, and this would be an example of our tonight forecast. Watch this, and then tell me, just as a casual audience, let's go from 7 o'clock tonight to 7 o'clock in the morning. What would you put in terms of a precipitation on this right here? Let's go from 7, and there you go. You've got stuff all over the place, and you get to 7 o'clock tomorrow morning. And notice how many areas of green pass through. I can go back. You can watch. Could you find 1 or 2 spots on this map that aren't forecast to have some kind of precipitation? Yes. Yeah, maybe down in Yates County, they got missed on a couple of spots, but there's not a lot of spots right there that are getting missed by some kind of rainfall in that overnight or late evening overnight interval. So that's part of what makes our job a living and breathing. Hey, I'll say it, not that way. It makes us very humble.
So,
Yeah.
so that's your mental averaging of all of this model
Pretty much.
to kind
Yeah.
of give a percentage probability for an average over the whole area.
Yeah, and that's what it ends up being. So that would be expressed in the confidence of the meteorologist that's giving the forecast too.
Okay.
Everybody would have their own interpretation. Like if you sat down at a trial in a courtroom, everybody would have a different interpretation of the events that came before and after. But most consensus lies in the middle, and that's what you're looking at usually on a 7-day forecast. Yeah.
When you draw frontal boundaries, are those frontal boundaries defined by barometric pressure readings or some other phenomenology?
Yes, they are. And here's an automated one, just for simplicity's sake. I'm just gonna have to find it on the fly here. I'm just scanning through right here. Okay. And so this is one that the computer comes up. Sometimes we draw our own. Sometimes if it's busy and it looks accurate to what we're talking about, we'll use one like this. But there's a trough of low pressure that I was just mentioning over Lake Ontario. It's the one that's producing the rain that we were just watching. So that kind of shifts on south of us by about 3 o'clock in the morning. Behind that, it's cold enough for lake effect, so the lake effect rain is continuing. But that would be a defining line, and you can see the kinks in the isobars also. Those are the grayish lines on there. Where a trough shows up, usually you get little kinks in the isobars, and you can pick out where the little trough lines are in the atmosphere. Now, around large high pressure, this will be the story for the next week or so. We'll be the Maytag repairman back here in weather going through the weekend and next week. There's not going to be a lot to talk about, but there's high pressure to the southwest, and notice how they're all parallel oriented southwest to northeast. So that's going to be that warmer air shooting up and paying us a visit later this week and next week.
So it's clockwise around a high pressure system. Wouldn't that bring in colder air?
On the east side of the high, it always does. But as this high, so this is Thursday around lunchtime, we're still going to be a little bit cooler than normal because we're still east of the high. But this high is actually going to break out to south and east of us by Friday, Saturday. So we're going to be quote on the warm side of the high at that point as it slides on by. Yep, that's a good question. Yep, and like I mentioned, I teach the course at Monroe Community College too. I've been there since 2001 teaching the intro. So all these different topics. And meteorology is the marriage of all sciences. So it's where physics and chemistry and even to a certain degree a little biology. It all kind of marries in with meteorology. That's why it makes it so much fun. Yep.
So you showed us the radar imaging.
Yep.
Is there any other type of imaging like satellite imaging that gets folded in and added to make the models?
Yeah. So this is a good example here. And these computers that we use have very high power graphics cards. I mean, if compared to a kiddo that was gaming, these things are these things. This thing is heating my leg as I sit here. I can just tell you that. So there's a lot of data going in. This is a satellite image laid on top of a NORAD image, but I can go through all the layers. If you look in the lower right hand side of the screen, there's a whole bunch of stuff I can throw on here. But there's the satellite layer gone right there, or I can shut the radar off and just go to the satellite layer and just show you the satellite picture.
And what wavelengths are available from the satellite?
Ooh, lots. This is probably just infrared right here. but this is a blend. So during the day, this is a visible / it's a hybrid. So this one will convert automatically to an infrared at night, and it'll be a visible during the day. So, but there's a whole bunch of different types. Let me go up here, and I've got a rainbow palette that I can use if I wanted. That's infrared also, but different color palettes. Visible is not going to pull. Oh, it is pulling through. That's interesting. So that's again pulling in the infrared channel at night. One of the hardest times to be a meteorologist is on the morning news, because a lot of times, especially in the wintertime, when it gets so cold outside, it'll confuse on the satellite imagery the cold air at the surface for cold cloud tops. And on a clear, cold winter night when it's -10, -15 outside, it'll start populating the ground with what it thinks are clouds, which are definitely not clouds. It's just cold temperatures being observed down at the planet's surface, and erroneously projecting clouds in spots that are just super cold. You can watch this in Canada like every night during the winter if you wanted to. Just go to NOAA's site and pull it up, and you can watch every night. It looks like there's a wave of clouds that goes through Canada as the air temperatures plummet when it gets cold outside at night. Yep. Yeah, so there's a lot of different color tables right there. Yeah.
So you have a lot of different sources. When we see the models of prediction of what's going to happen and
Yeah.
where it's trending,
Yeah.
do you have any idea which of the many sources are used as input?
We pick the ones that we want to use. So I could comfortably say on the air that I would know if it was the North American model, if it was the global forecasting system, the GFS. You hear a lot about the the European model that goes out there, but there's tons. The one that I showed you was the IBM, a very high resolution model. But we know exactly which model we're using, and you'll be amazed if you load up different data sets. I can go to back to that image that I was just showing you, and let's edit this quick, and we'll go into the precip layer. Of course, it popped up on the other screen. Let's come back over here. Here we go. Okay, so we're over here, and I can go to my precip type layer, and you'll see this pop up on the right. What's loaded right now is the graph 4-kilometer North American high resolution model. But just to give you a rough idea, here's a number of data sets. There's the Euro 9-kilometer, the HRR, which is a rapid update model. The GEM is the Canadian. That's a 10-kilometer high resolution. The GFS is the global forecasting system. Graph is what's loaded. The HRR CONUS, which just does the United States. NAM is also a model that just goes over the United States, 20-kilometer grid scale there. Basically, the smaller, tighter the grid scale, the more data you're getting in a smaller area. Essentially, things like the barometric sensor in your iPhone or your Android get used on some of this stuff. They take data from personal weather stations, local New York State Mesonet, for instance, that's across New York State now, to take pressure readings off of that, and all that gets injected into the modeling now. So they take in tons and tons and tons of info now compared to when I started 25 years ago.
Do you know how often the model that you prefer using, how often it's updated?
It's every 3 hours. This one that you're looking at is every 3 hours. So I'll get 8 updates on this in a day. Sometimes it's a little maddening because we'll always set it to take in the most recent data, which is almost always, but not always, almost always the most accurate in weather. But we'll be on the air sometimes, and it'll be, our weather will come up at 10:15 on Fox Rochester or 11:15 on ABC, and the new data set will have come in. Well, oftentimes you don't have. There's only so much time to scan through and see what's changed and what's coming. So sometimes you'll have some big changes over a small period of time on some of these data sets. More often that happens during the summer in convective weather, like thunderstorms and localized severe weather. And you'll see some big run-to-run changes, and you'll be talking about one thing, and then you have to incorporate the new information that's coming in a very short period of time, or sometimes it'll even catch you on the air, and that's a little interesting. Yeah.
Thank you.
Yeah, no problem.
I'd like to open up to everyone else who's got any questions or comments they'd like to make. We have a great opportunity here, so please take advantage of it.
Yeah, I've got a couple of more minutes if anybody else has anything else. Yeah. Sorry, I was a little late on the initial call there.
Did you see in the chat there, Mark? There's another question.
Oh, yeah. Is the raw data utilized and max available to the public? So this information, this is a proprietary program that's developed specifically for meteorologists. So this would be, yes, available for purchase. I'm not sure how much they would charge. So this would take all of the data sets that are available and you would have them. All of the information that is on Max, I would bet, is also available in some kind of public forum. Okay, but you would have to go straight to the National Weather Service, the National Climate Data Center, NCDC would have, all the data volumes of everything that's out there for sure. Yeah. There are a few colleges even that have it. I know Oswego had it briefly. I don't know if they still do. They were using it for their meteorologists in training. They have a TV station, WTOP there, and they were training their meteorologists with the data that was coming in off of the system. Yeah, it's a good question. Yeah, it's a great program. There's nothing that as long as you can think it, the system can do it. It's incredible. It's incredible. There's really no limit on what we can do.
Absolutely fascinating. Mark, thank you so much. We really appreciate you having a very long day. If you're filling in for Scott this evening and shift gears so quickly and develop this on the fly, we really appreciate the time you spent with us. Thank you so much. And thank you everyone who attended this evening. Appreciate your showing up.
Thanks everyone. Have a good night. Okay.
All right. Bye now.
Bye.
Did have one more question off the record. What's your definition of normal?
Okay, normal is a setting on the washing machine. That's my definition of it. But no, normal. So we have climate normals, and basically we use a 30-year data set from the National Weather Service in Rochester. So they have the sensor at the airport, of course, the station at the airport. We're on the 30-year data set, 91 to 2020 right now. And we'll use this data set until we'll be not 91, we'll be 2001 to 2030 will be the next one, but we won't start using that until we get to the next decade. So, and of course, things change over periods of time. There's been a gradual warming recently, but you can go back through periods that were gradually cooling too. If you go back to the 70s.
So on the air, when you say temperatures are above normal.
Normal would be the way to say it, not average. Okay. Because it's a climate normal. Oh, sorry. Go ahead.
Why not the word average?
Because it would be a climate normal based off of that 30-year data set. Okay. Yeah. Because any particular day, let's say for today, you can see the variations over time here.
You're not sharing at this point.
Oh, I'm not sharing. Well, then you can't see anything. That's not fair. Okay, let me do that. Let me do that. There we go. Share a screen again. There we go. Now you can see it. Okay, and then here we are in October. And you're looking at your data sets of all-time record highs and lows through that period. And then they have what's called the daily climate summary that comes out. And
so to me, normal means what you would expect to have over this 30-year period, 95% of the time. You've got some tails where you've got some extremes.
Yeah.
To me, normal is what you would expect 95% of the time.
Yeah. Yeah. And you can see the line that they have here. There's the climate normal. Yeah.
So when you say the temperatures are above normal, does that mean we're in the tails, we're at the extremes, or does that mean we're above the average?
Yes, that means that you're towards the extreme. So for tomorrow, for instance, the normal is 61 and 43. So we're going to get to 47. Basically, and this isn't the case for every city. I would
but-
say we're close.
Sure.
If you went into like statistics or something like that, mean, median, mode, you know the deal. About every 5 degrees is one standard deviation for us. So if you got a high temperature tomorrow at 47 and the normal is 61, that's almost 3 standard deviations, which is, you know, when you're looking at statistics, that's a pretty low probability event.
Well, that's interesting, the 5-degree% deviation. I'm going to watch the weather all differently now.
Yeah,
Yes. Yeah.
don't ever ask a meteorologist, you know, about the percentages, you know, when they're giving a forecast, or if you hit on social media, because once you put that out there, everybody has this wildly different view. When you see 75% on the 7-day forecast, somebody thinks that it's going to rain 75% of the time of that day. There's no doubt about it.
Yeah.
Yep.
Again, thank you very much.
Yeah, no problem.
You've had a busy day.
It's fun.
Thank
It's
you.
fun. It's always, every day is different when you're a meteorologist, so that's the fun part. Good night.
Very good. Thank you so much.
Okay, thank you.
Thank
Yep.
you.